aspects of surface reactions in solid surface and photo-induced reactions on semiconducting materials with applications in indoor air cleaning, self-cleaning, and water cleaning. He is also the co-founder of the Swedish Society on Vibrational Spectroscopy. He is also a CEO of the spin-off company Molecular Fingerprint, board member of the Uppsala Center for Photon Studies, the International TCM Net, and is the vice chairman of the International Science Program. Today he is going to talk to us about photocatalytic materials for off-grid ultrafiltration of water. So please, Professor Lars Österlund, welcome. You can share your screen and
you need to allow me to share the screen first. Thank you very much for your kind introduction. The host needs to allow me to share my screen here. Is it possible?
yes.
Thank you. Thank you very much. Thank you. There we are. So I will just start my presentation here. And then starting from the beginning. Thank you for your kind introduction here. For the next 30 minutes, I will give a presentation of photocatalytic materials for off-grid ultrafiltration of water. So my name is Lars Österlund. I'm professor at the Solid State Physics Division at the Department of Material Science and Engineering. The reason I will not look into your eyes completely into the camera is that my screen is on a different location, so you need to forgive me. So Uppsala University, Sweden. I love to be in Nairobi at this time of the year, but circumstances, as you all know, has prevent us for these meetings. Nevertheless, we will try to do our best and cope with the situation. I will start off with this outline of my presentation. I will have 4 sections in my talk. I'll talk about advanced oxidation processes just very briefly, where I will place this ultrafiltration into a context, show the potential mainly, just to a very sketchy. Then I have 3 subtopics: textured titanium films, where I'll talk about what are the problems really, and how can we understand a catalytic material which is supposed to function at ambient conditions and be able to oxidize molecules, which is primarily a goal for water filtration purposes. And then I will go a step further, and can we do something apart from modifying the actual structure to chemically modify them? And I'll talk about acid modified surfaces. And as a final section, I will talk about possibilities to combine different materials to make heat reaction structures, and to addressing yet another problem which we know from the fundamental research on just simple photocatalytic materials like titanium, which is the most abundant. And then I will talk about something about solar mediated photocatalysis and how we can exploit solar light in a more efficient way. And I will call this spectral selective multilayer coatings. These are some pictures which will reappear to the right here in my presentation. So photocatalysis in a short terms, which is the title of my talk, it appears quite deceptively simple. I mean, you put some material into the water in this context, and then you shine it with light. And even sunlight is sufficient to mineralize most organic compounds. And out comes simply just water and CO2 if it's completed. And this has been known since more than half a century. And especially since the 1970s, a lot of research has gone into this. And yet we don't really see a a large-scale deployment of this. And on the left-hand side, on the right-hand side, you can see a lot of pros with this technology. And you can list them apart from being able to do what they are supposed to do in this context for water cleaning to remove all the UCs. Also, the important class of recalcitrant chemicals of emerging concern, CSCs, including dyes, which I will show you examples of. Only water and CO2 as reaction products, mild conditions, no after treatment ideally is necessary, energy efficient, environmentally friendly. You don't add a lot of chemicals as we do normally in the centralized systems we have, for example, in my country, where you need to control the process very carefully, but it works immensely well. So this is the predominant technology. And this technology, it promises decentralized off-grid solutions, and it's cheap. So why don't we see it to the more extent than we do? That is something I will address in this talk. But the promises lately, I would say the past 10 years, has been a renewed interest, not only in photocatalysis, but advanced oxidation processes in general, to put them into more decentralized modular systems where, for example, point sources can clean completely with zero discharge water for recirculation, reclaiming water. And there are even propositions. I took just some simple examples from very, very recent unpublished literature where they even supposed to have this closed cycle loop for also for the biodegradation part where you can harvest this piece in a special biodiesel process. If this is sustainable or not is another question, but the point here is this modular decentralized loops is becoming with zero discharge claims is really something which is emerging again today. Of course, driven by the needs, regulations, and sustainability issues, which is becoming so important for the world. Now going into more detail, that you can maybe have a look here that it's not so simple as it appears. This first of all, introducing the concept of advanced oxidation processes. This is a whole class of processes where you do oxidation chemistry by several means. We meet it in many cases where we have heavy load of pollutants, even in centralized systems where you add ozonation, even UVC treatments. Photophantom where you add, for example, iron and hydrogen peroxide. This is common and this is also commercialized. Photocatalysis belongs to this advanced oxidation process, where in this slide I more particularly introduce this titanium dioxide, which we'll spend some time on this lecture, where you do both oxidation and the reduction. And here, importantly, the oxidation process I'm talking about is the oxidation of an N-type material. The valence band is sufficiently deep to be able to oxidize most organics. So this is this N-type oxides like this simple titanium and zinc oxide and so on. And they are oxidation catalysts primarily. This is the virtue of these materials, apart from their chemical properties. And oxygen plays a role here of just closing the loop for the reduction purposes. So this is the context where it is spent. So produce water, you have some pre-treatment systems always necessary. You may have some necessary osmosis process in the end, but they are modular and quite small, and they can produce up to commercial AOP modules which are sold to companies, particularly pharmaceutical industries or some other point source pollutants. Today, they produce up to 25 cubic meters per day easily in these modular designs, but not well spread in the society. So I said the pros here, some cons here of the heterogeneous photocatalysis, as it's called when you bring one medium water into contact with a solid state, is that you have a lot of challenges here, and these are the reasons it's actually not implemented in the larger extent. Here's an example. This is actually gas phase, which you look from the left third picture. You flow gas, acetal is shown here. You can see initially we have a huge drop of the pollutant concentration as you want, and then it gradually decreases. This is a deactivation process. Something happens, and this is usually when you have a surface and it occurs at low temperature, is that you're typically kinetically limited by desorption or even deposition of some strongly bonded intermediates here. So you actually populate sites and eventually become covered, and it doesn't function as good as it did initially. Another thing is this low efficiency. This is inherent in most of the system, that you excite electrons across the valence to the conduction band, and these are the hot electrons which they do the job, and the holes they oxidize, which is left behind. And this, the most efficient process is actually recombination here, and this is something you need to solve if you want to speed up the efficiency. And so all this in yellow, these are really the disadvantages with this technology as we mostly have seen today. And of course, the past, I would say 10, 15 years, there's been a tremendous development in materials. And I will highlight a few of these approaches in this talk. So going to one of these, I said deactivation and bonding of strongly intermediates, which eventually can block a catalyst at low temperature. In water, this is less of a problem than in gas, but still, even in water, this does occur, that you have a very strong bonding. And as you are familiar with this more than 100-year concept of Sabathier's principle, the principle of moderate bonding, if a catalyst should work, then it should bind the reactant molecules. This is how you transfer electrons to make and break chemical bonds. On the other hand, if it becomes too strongly bonded, it sits there forever, and then you are actually poisoning the catalyst by site inhibition. And this occurs at low temperature typically, and that's why most catalysts in the industrial process, they are operated at high temperature in most chemical processes. Photocatalysis is inherently a low temperature process as it's designed today. And we have this ubiquitous material, titanium dioxide, which looks like this. This is a crystal structure which you can find in nature of the anatase crystal. You can cut it in different forms, and you can do it synthetically. As it happens, when you start to moderate with this texture of the crystal, you can actually moderate the amount of these strongly bonded intermediates in a typical reaction. And this is shown on the right-hand side here. Depending how you cleave the crystal and the facets which are exposed, you can actually either get it very quickly poisoned, or you can actually have a sustained activity. So, and this has to do with Sabathier's principle of that you actually expose sites which are more or less prone to deactivation. And this has been known for many years. One of the first examples, actually 2002, a Japanese group did this. And since then, there's been a lot of development in this field. Just to articulate what I just said here, in many cases, when you decompose VOCs, you end up with typically molecules which looks like this. This is usually one of the final products. You end up with carboxylic or aldehyd-like end groups at some point. And these are depicted here graphically in red. And here you can see with the operandi FTIR spectroscopy how they build up on the surfaces as in the course of reaction. And as whenever you have crystal structure, for example, rutile or other structures with which are common, you build up these kind of species which inevitably eventually then poison the catalyst. But on the left-hand side, you can see actually you can actually do better. It is possible to expose crystal structure which actually they do a better job. And so to summarize this, we know that in many of these VOC photooxidation products, you end up with these small molecules which has a tendency to form these coordinated compounds, which is very difficult to get rid of under these mild conditions photocatalysis is operating under. So knowing that these RDS means rate determining step, if you know this, and you have also knowledge on how they form, and you know also the role of defects, which I will not talk about here, you have the possibility to tune the surface facets or the surface texture. And this afterwards we'll just discuss here. What we have done is that we have used magnetron sputtering technology and come up with a scheme how to orient the surface texture of these films. And as you may know, sputtering technology is an industrial process. This is one of the major processes to make thin films. So this is clearly an upscalable technology. And these electron microscopy images, this is how it typically look like. So from there, you cannot see the surface texture.
Clear and at times it breaks.
Yeah.
It's okay.
Was there a question here?
If it breaks, because the
Is everything okay? Shall I continue? I cannot hear you.
Please continue. Please
Yes,
continue.
Thank you. So what you can see here, forgive for this interruption. There was a question online here, which I didn't really catch. But I continue here. This is a busy slide with a lot of questions, which I will not discuss. But what the message here is, if you start with the XRD pattern here, is that depending on how you prepare it, you can get a larger fraction of 001 orientation of the films. And this can be tuned by reaction conditions, which I have explored in these publications. And this plot here, it shows the probability that you have something else than random structure. So the red curve is a signal that you have something which is preferentially oriented. And this is actually comes at an angle to the surface normal here, if you do the calculations here. But this is knowing this and knowing that you can actually then tune how the surface is terminated. That is how the exposed surface facets looks like. And knowing what I said before, that you can actually use this to moderate the bonding of key intermediates, then you can use this technology to improve the sustained activity, not the initial activity, but the sustained. And this picture just shows an example of how we have oriented the films. So 36% of the surface is oriented with the 001 orientation. And look on the y-axis, the scale, compared to a commercial film. That is 1,000 times more effective in terms of rate in absolute numbers compared to commercial films, which has nanostructures and it's absolutely not optimized for these conditions. And we can understand this, and we can, from the random to the oriented phase, by analyzing details of these surface reactions. A conclusion is, apart from the quantitative numbers, which is listed here, is that you can actually control the relative humidity and the catalyst temperature, and of course also the surface texture, to optimize their activity. So we have come up with a scheme how to prepare films on a large scale potentially, where you have a sustained higher activity, avoiding this deactivation mechanism. So this comes to the end of the first part here of how to make materials with sustained activity. Still, they are not super active in terms of efficiency, and still they are prone to some deactivation, as you also noted in some of the slides. So then I will turn to the next part of my presentation, which is surface functionalization. Here again, coming back to the theme of my presentation, idea is to block a combination of the inhibitor molecules and do it by a chemical mean. We have a scheme, a methodology where we actually prepare a film. We can do it with the methods I just explained, sputtering, or it can be wet chemical. And then we have a process where we actually photoabsorb SO2 molecules, or actually other molecules of interest. And these are further reacted to sulfates on the surface, and thus very strongly bonded here. So you cannot wash them away or even sonicate them away or with ethanol cleaning, they remain. And as you know, when you have a low acid surface, you have this quite nice properties, being, of course, having this low pH, you have this proton-mediated reaction transfer mechanism occurring. It has some really interesting oleophobic properties that is simply possible to stick grease on the surface. And it has this properties 1, 2 here for long-term sustained activity, because it decreases surface deactivation, because this provides then a proton reaction channel to mediate surface reaction, as I will show in the next slide. And on top of that, it happens that these bind on the sites which are prone to deactivation. So it's a balance. You lose some of the initial activity because you block some sites, but you gain the sustained activity. And we have explored this method how to make these surfaces super acidic. It should be known that sulfated titanium is a known catalyst. It's prepared by quite harsh method in powder forms, and we have now come up with a scheme how to actually make them synthetically on the films under very mild conditions. And these are the publications here, also well been in my slides, which I will distribute to the conference here, how to make sulfated titanium with these attractive properties. But given the circumstance that you have these sulfated titanium surfaces, what you do is actually that you bind them on the sites which are other prone to deactivation, and then you mediate this proton transfer reaction to facilitate reaction. You lose some sites, but you gain the long-term activity. So this is quite nice, and then working water as well. Just to exemplify what I said about the Sabatier principle, if you remember, many of these VOC oxidation processes, they are prone to this deactivation process due to this bonding of these molecules. And this is actually a 3D graph of picture as shown, where we do operand FTIR and show that these build up. And these are the vibrational signature of these species here. And you don't want them because they have built up. And if you add in sulfated titanium, you can see that these simply doesn't build up. They don't build up on the surface. And indeed, we have a sustained activity on these catalyst surfaces. Another just a practical application is that there's oleophobic. Here's a common titanium film, and here's sulfated titanium. And this is again an IR spectra showing the stearic acid signature, which you coat it. Stearic acid is like a mimic of a fingerprint of grease. It's a model substance also used for ISO standardization purposes. And this is simply not present when you have it sulfated. It doesn't stick at all on the surface. And you can do anti-graffiti coatings with these kind of coatings as well. Simply is very good for self-cleaning purposes. And as you may expect, water absorption is also reduced, showing here. This is actually an example with a coating on a cement product. So this is, of course, one way to do it, that you modify the texture of the catalyst, that you add some chemical and some molecules at its surface to combat these deactivation problems. But still the efficiency is fairly low, as I said initially. So one strategy which is common, and many are, I would say that majority of the research being conducted today belongs to this class, which is my last section, where they chemically, by doping, try to modify the structure of the catalyst for many purposes, both for reducing electron hole pair recombination, as we do here, but also for visible light activity to exploit a larger portion of the solar light. I will focus here on reducing electron hole pair recombination. If you remember, as I said initially, a photocathode works by an interband transition. You have a semiconductor where you, which absorbs light, typically in the UV region for titanium, maybe also a bit in the visible blue if you have a visible light catalyst. But and then you form these hot electrons and leave a hole here. And most N-type semiconductors, here this valence band is quite deep here, and this hole is very, very potent oxidation for oxidation reaction. even more potent than ozonation or hydrogen peroxide. So it's really very efficient for oxidation processes, especially with titanium dioxide. This is why it's so successful in its oxidation processes. This wants to recombine this electron hole pair. So one way to do it is actually to use this semiconductor physics concept of placing a p-type and an n-type material close to each other and let the electron hole pair separate across a boundary where you have electrical contact between two materials which are either p-type and n-type. And this is what I will discuss now. I will show one example where we place copper and zinc together and see if we can actually get this to work. And then you do the oxidation reactions on the p-type and then the reduction on the n-type. So this is what it will look like. So ignoring the numbers here, the numbers are of course important if you want to place the energy bands in a proper position and choose your catalyst material. But the note here that here you have a p-type, you have the thermal level just above the valence band. Here you have an n-type, even straddling the conduction band for zinc oxide. When you place them together in contact, you have charge belonging to zinc to copper, and in our case we have copper to oxide, and you have this band structure being formed where we have a region in between, which is then the region where you have this charge separation. And when you start to eliminate such a system, you have the possibility to separate the electron hole pairs simply because the electron is then transferred across to the zinc oxide in this case and holes to the copper oxide in this case. So this is the semiconductor physics approach to separating electron hole pairs, which is used in many devices you find around us these days, from diodes and so forth, photodetectors and so on. The important thing here is that actually the numbers here. You need to place them so you're able to do the chemistry you want. You want still in the photo cleaning, water cleaning purposes to have the holes sufficiently deep to do the water cleaning, and the oxygen, if you have oxygen as a reducing agent, then you want this to straddle the oxygen levels. So there are some band alignment work to do. We did this for this system, copper to oxide, which is a p-type, and zinc oxide, which is an n-type. And this is the scheme and the numbers for this system. And what we did here, this is collaboration with Taltech in Estonia, is that we actually deposited on zinc nanorods copper oxide. So this is a bare zinc oxide nanorods, and here they're covered with a technique where we actually land small clusters of copper particles and oxidize them on the surface of this zinc oxide. So this is an electron microscope, so you get a picture of what we are doing. And we formed this PIN structure, this junction, shown by both photoelectron spectroscopy and photoluminescence. We have a shift here in the zinc states and also in the Auger transition of 0.3 electron volt, pointing to a charge transfer from zinc oxide to copper oxide, as I indicated here. This would we expect to occur. And this is also evidenced with arguments, which I will not go through here, with the photo emission spectra here from photoluminescence measurements, that we actually are able to quench zinc oxide emission bands. So this is a clear indication that we have charge transfer occurring across this electrically contacted copper oxide to the zinc oxide nanorods. And indeed, the activity here, this is shown for orange dye, a common recalcitrant dye. This is then the absorbance as a measure in situ, actually. We do it while we are running the water cleaning process here. And this is just the lowering of these curves means that we are losing orange dye concentration. And as you may appreciate here, this heterostructure has the fastest degradation rate, and this is also shown in this plot here, first order reaction kinetics, that this group of experiments show a clear favor for this heterojunction system, taking care of surface area and so on. This normalization you need to do. So if you put numbers to this, the quantum efficiency is increased by 65%, and possibly this is just one way to do it better in terms of this efficiency. So having said this, I have basically discussed these three approaches for improving a catalyst by modifying the texture, the surface structure, pointing us to the common titanium dioxide, how you can improve that by knowing the Saboteur's principle and how the molecules bond and which are the rate-determining steps. I've discussed chemical means, what adding sulfite molecules to improve the reactions on the surface and elevate site inhibition. And finally, this electron-hole pair recombination issue, where a heterojunction may help to reduce the recombination across the boundary. Finally, I have just a few minutes left here, is that I will show one example where it can be a bit smarter utilizing the light source. In many of these propositions for photocatalysis, solar light is the light source of choice. And actually, if you want to use UV light, it's just 4 or 5% of the total solar light. So what about the rest? Can you use it in a smart way? I have sketched one possibility here. If you place the photocatalyst on top here, and then this is called transparent for the rest of the solar light, and then you have a heat-absorbing film underneath, which actually become hot, then you will heat this photocatalyst and improve then the surface kinetics, which is of course in many cases Arrhenius type behavior, so exponentially in terms of temperature. So this concept, where we actually had a thermochromic film for a heat absorber and a titanium on top of this, was realized in this concept, where we placed titanium on vanadium dioxide. These are just electron microscopy images, AFM and XRD images, proving the structure. And this is the optical properties showing that in the hot state, the absorbance of a near-infrared light is higher on the vanadium dioxide film. This is a busy slide, but just believe in the numbers here that they are absorbing more heat into this VO2 covered film, these guys here. And we can see it again in this belay structure, then again appreciating the decreasing absorbance here, again a probe molecule as a function of time, and it decreases faster on this belay structure. And this is the configuration here, that in this belay we are probing having a probe molecule with this carboxylic end groups and solar light, and then we have faster activity. And with this concept, you can actually increase it twofold. Then going to a solar absorber, for say for a water cleaning system, you place here a perfect solar absorber which becomes really hot. Then you can improve the same reaction rate by easily a tenfold increase of the quantum yield. So this is clearly a possibility. And this shows the number for absorption coefficient, the emissivity of these coatings. And this shows how the film temperature is increasing up of solar heating. And it becomes really hot, and you actually improve the quantum yield by tenfold. This is a lot. So this leads me to the final conclusion. And again, I will summarize what I presented very briefly. In each case, I showed some publication which you can read for further studying these subjects in more detail. I have taken a material science approach, how the different bonding of intermediates affect the total sustained activity of titanium dioxide, balanced bonding to low coordinated titanium atoms, and protonated oxygen sites is important for activity, and ways to improve this with structuring or orienting the crystals in a good way. We can tailor the surface acidity, have site protector and proton source with some really interesting olefophic properties. We can do this heterojunction B catalyst, where it can help to avoid or improve the electron-hole pair recombination, which is one of the reasons that, for example, titanium is quite poor efficient catalyst. And this is the example then of this nanorods covered with the copper oxide. And then if you explore and use solar light, you can actually exploit more of the light source and actually enhance the catalysis by having, for example, heating one part of the system and doing chemistry on one part of the system. So this leads me to the conclusion of my talk, and I think I'm running out of time as well. And as showing the acknowledgement, of course, I didn't do this work myself, and this is a list of my colleagues and co-workers in this for all these studies. And also on the right hand, you see the funding agencies for this work. So thank you for your attention. You need to unmute yourself.
Professor Mamburi, you are muted.
Oh, sorry, I was muted. Thank you very much, Prof, for the very nice presentation. Now, I was saying that I'm going to use the next 12 minutes to invite discussion on this topic. So the floor is open for discussion, please. Yes, anyone? Anyone with a comment or question?
Yeah, I can start. Hi, Lars. Thank you for the nice talk. I have a question about, perhaps because I'm a bit more of an engineer, I have a question about stability. So when you have your sulfur oxygen groups on top of the titanium dioxide, can you say anything about their long-term stability and when they're undergoing photocatalysis?
Yeah. First of all, the binding energy of these sulfate group is 2.8 electron volts in the physics world. So they're really strongly bonded. And from a practical viewpoint, you can easily wash the surfaces with ethanol. You can do the typical disinfectant you do in hospitals. You can sonicate them. So that is possible. Of course, you can. We have not done really long-term stability measurements in other media, so I wouldn't know that. But just guessing what you could do, I wouldn't suspect that they would be sustain all kinds of treatments.
Okay, cool. Thank you.
Thank you for that.
Yeah.
Any other comment?
Can I ask a question?
Yes.
Thank you for good presentation. My question is on slide number 19.
Wow. This one.
There's one with the two diagrams. Yes, this one. Upon interband absorption, there seem to be formation of VOC. The issue is coming from where? Because the diagram to my left, it is showing upon electrically conducting the particles. Because I was expecting the VOC to be formed during when it is electrically conducting, but upon interband absorption, you can see with that one, there is actually the formation of the VOC.
Okay. So this is just a diagram showing the energy. So this is an energy scale on the y-axis. I apologize for this. This is just an energy diagram. And on the left-hand side, you have two isolated compounds. Copper oxide is not contacted with zinc oxide. So this is what is the energy diagram of the electrons, how they are positioned in terms on an absolute scale from the vacuum level before they're contacted. Then you put them in contact. Then charge flows from zinc oxide to copper oxide. And then of course, the Fermi levels need to equilibrate. And this is what happens on the right-hand side. And in addition, on the right-hand side, I've shown what happens when you start to absorb light, which is above the interband transition edge for copper oxide in this case. In our case, we've used actually a 365 nanometers, which means that we have an interband absorption both in the orange part and the blue part, zinc and copper oxide. And I added these arrows for you said VOC, but the oxidation reaction and reduction reaction here, just pointing that where the oxidation and the reduction reaction occurs in close these interfaces. So this is not a chemistry; it's just placing two semiconductors close to each other and then electrically connect them.
Thank you, Lash, for that. Kindly, when you make a comment or answer, introduce yourself and say where you're from. That was Professor, I think, Robinson Musembi from University of Nairobi. Can we have any other comment or question? Prof. Aduda, I see your mic is on. You have a question?
No. Sorry.
Yes. Okay. Okay. Otherwise, then, thank you very much, Lash, for the very nice presentation. And I'm sure if there are other questions or comments, people will put them in the chat. Please feel welcome to put a question or comment on the chat. So we go to the next presentation, and our next presentation is going to be by Professor Richard Bryce from Wellington, New Zealand, that is Victoria University, Wellington, New Zealand. Oh, he was at the Victoria University, New Zealand, but now he's at Karlsruhe University in Germany, Karlsruhe Institute of Technology in Germany. His primary research areas lie in the third generation photovoltaics, that is including perovskite solar cells, spectral conversion, that is up-down conversion, luminescent materials, light management, and solar-powered water treatment systems. So I wish to welcome Richard Bryce. You have 30 minutes for your presentation, and then we will have 15 minutes for comments and questions. Welcome, Richard.
Okay. Thank you, Julius, for your kind introduction. Let me just try and share my screen. You should be seeing that now. Slideshow. Okay, hopefully that looks good at your end. So yeah, like Lars, I would like to join him in thanking the organizers for this invitation to talk at this Msseesa conference, and also to share his slight disappointment that we couldn't travel to Nairobi to be with you in person. Let's see what opportunities there are in the future. So I like to thank Lars also for giving such a very nice background to photocatalysis from the sciences level, because I'm going to build on that more from an engineering side. So I'm going to be talking to you today about atomic layer, deposited ultra-thin titanium dioxide layers, which are coated not only onto but also into ceramic membranes that we then use for photocatalytic water treatment. This is work conducted by myself within the Institute of Microstructure Technology at the Karlsruhe Institute of Technology. And also the other half of this work is Professor Andrea Schäfer, who is also my wife, and she is an expert in membrane technology and also at the same university. So, very brief geographical introduction for those of you who don't know Germany. We are down here in the bottom left, so that means the southwest corner, near the French border. That's where Karlsruhe is lying, and we are somewhat unique in Germany because we are a merger between a technical university and a national research lab, and this merger happened in 2009, which means that we now have 9,300 staff, so a huge number of staff, and 26,000 students, which is...
Excuse me, Bryce?
Yeah.
Sorry, Bryce.
The
Maybe
slides,
you can put the presentation mode on your slides.
It should be.
So the slides doesn't come out here.
Hang on. Well, I have sharing. You are screen sharing.
Maybe you can put the presentation mode at the slide mode. Yeah.
Yeah. I have.
Yes. And the full screen, full screen.
What are you seeing now?
We can see all the slides on the left.
So in slideshow.
Slideshow, yes.
Yeah, but from my end, it looks like I have started the slideshow.
Okay, I think the current, yeah, it's okay now. It's okay now.
Really?
Yes. Yes.
I changed nothing.
Okay.
Okay. Oh, we are from an Institute of Technology, but we can't do Zoom apparently.
Yeah.
Okay, so that was a brief geographic introduction, where we come from as a group. We are a multidisciplinary group. We have chemists, physicists, engineers in solving problems, as Julius mentioned at the start, relating to material synthesis, the characterization of these, and the use of these in fields like photovoltaics, and now more recently, photocatalysis. Examples of research that I've just taken as a snapshot from our website. So we do nano and microstructures for light management strategies, materials for spectral conversion. So that's converting wavelengths of the sunlight in particular into different colors, both up and down conversion. Optical spectroscopy plays a large role usually in characterizing our materials. Perovskite photovoltaics, the new kid on the block in terms of the photovoltaic materials, but also very promising. Novel concepts. When things work at the science level, we like translating these up to the to small 10 by 10 centimeter photovoltaic modules. But today in the bottom right-hand corner, highlighted in yellow, is what I'd like to talk to you about, and this is our research on solar-driven water treatment processes. So before I start, just to highlight the other half of this research effort. So I'm the solar energy expert, and Professor Andreas Schäfer at the Institute of Advanced Membrane Technology is the water treatment expert. So they're just briefly highlighting some of the expertise coming out of her institute, and it's really the putting these two things together that gives some quite unique results that I hope I can show you. Okay, I guess that's the introduction is done. Let's set some of the background here. So what we have is organizations like the World Health Organization telling us that about 1 billion people have no access to clean drinking water, and this means that something like 1,000 children are dying per day. And a great majority of these, over 600 million, are residing in sub-Saharan Africa. 67% of these people have access to what is called an improved water source. This typically means that there is a good foundation and that no runoff can go into the well or the borehole where water might be pumped out of, but it doesn't mean that the water is treated by any means. And there is this catch that there is a lack of electricity available in many, at least remote parts of Africa as well. And that I've shown here the link between these in a figure taken from a paper where the x-axis and the availability of an improved water source on the y-axis. And despite there being 200 data points and quite a bit of scatter, the 200 data points being the nations of the world, you can actually see that there's quite a good correlation between if you have electricity or not, then you are likely to have access to clean water or not. And this is one thing we refer to as being this energy-water nexus, this intertwined nature of these two commodities. So what would we like to do about that? The solution I've highlighted down there, we're seeking to develop small-scale, decentralized water treatment systems that are powered by solar energy. And we believe that these can have a very positive impact on development goals in the areas of water, energy, gender equality, education, etc. So just some previous experience. I was on an extended sabbatical in Tanzania from late 2012 to early 2014. The first half of my stay, I was hosted at the University of Dar es Salaam with my friends Margaret Semiji, Nura Muluka, and Letiko Makusa. And the second half of my stay, I was hosted at the Nelson Mandela African Institute of Science and Technology based in Arusha. And there, what we were doing was very much engineering-oriented field research. We were looking at fluoride removal, which is a common contaminant in the northern Tanzanian region. And if you look at this system shown on the right, you see a trailer-based system. It has 300 watts of photovoltaic panels, and it's equipped with two membranes, an ultrafiltration and a nanofiltration membrane. And it's simply the photovoltaics directly powering the pump can produce about 1 of clean drinking water per day, or I should say per solar day. So while that worked quite well, there's a bit of a materials emphasis lacking there. So that's taking engineering components off the shelf. But what can we do with photocatalysis? So largely this slide Lars has already covered the principles of. So we're using wide bandgap semiconductors to absorb at least the ultraviolet, hopefully some visible light. This electron hole separation shown on the right can be used to drive chemical reactions, both oxidation and reduction. The most commonly ones known, titanium dioxide, zinc oxide, iron oxide, copper oxide also there as well. We are going to be talking about today using titanium dioxide in the anatase phase, and the band gap of this is 3.2 electron volts. Now, the overall goal here is that we want to achieve photocatalytic degradation of contaminants in water. This could be achieving disinfection, looking at getting rid of hazardous organics, as well as things like pesticides. And the main amount of work that is done by our titanium dioxide photocatalyst here, we don't have direct proof of this, but we suspect it's the hydroxyl radical ion that is the main reactive oxygen species present and active in our material. So when we look at these systems as engineers, you have a number of different types of photocatalytic reactors, and they could be either based on particles, as shown on the left, or they could be based on immobilized photocatalyst layers that are shown on the two right-hand examples. And ideally, in a photocatalytic reactor, what we want to achieve is we want to have a immobilized photoactive material. Sorry, there's a spelling mistake there. We would like to have a high surface area because that's going to give us, that's going to drive our chemical reactions better. And ideally, we would like to be able to operate in a single pass continuous flow mode. So this means not in a kind of batch system that you just have to leave it, which is not very compatible with scale up, but we would like to be able to be keeping passing liquid through this system and it being treated the whole time. So we built a system. There's a schematic of it here and a photo is coming next. It's relatively simple. There is a single pump sucking liquid shown here as our feed, which contains methylene blue dye, which was used as a model pollutant. Concentrations are typically about 1 milligram per liter. And then the water is, this contaminated water is pumped through a photochemical cell here, where we have a membrane and a quartz window shown in blue. And above the quartz window, we have a UV LED. I think it's the same one that Lars was using, a Thorlabs 365 nanometer light emitting diode. And then from there, we can measure the amount of permeate, which is our clean water, using the similar techniques to what Lars demonstrated for the orange dye. Here, just looking at the inline UV-Vis spectrophotometer to tell us how much light is absorbed in that region, thereby giving us a concentration of that dye, and deliberately shown here as being somewhat lighter in the permeate than was originally present in the feed. A schematic of the setup is followed by a photo here. The really interesting parts, the zoomed out on the right. So there we have this high power UV LED in black and red, which is then bolted on top of a stainless steel cell. And on the very right hand side, you see the stainless steel cell opened up, and you can see that we have a place for a membrane here, and you can also see the quartz window on top. So which membranes are we using? With this work, we initially started by using ceramic membranes. These are anodized aluminum oxide membranes. We chose these because they have good thermal robustness. This means that they will survive our later calcination process for the titanium dioxide. And they exhibit a near cylindrical pore structure. So probably clearest shown on the top left SEM image, where in the cross section there you can see a somewhat defected but quite nice pores running up and down the edge of this membrane. We chose to investigate two different membranes. So we bought membranes from Wattmann and also a German company called Smart Membranes. And these were given also in two different sizes. So we have 200 nanometer diameter pores and 20 nanometer diameter pores. And I think I forgot to mention before, the membranes are 25 millimeters in diameter when they fit inside that cell, and 60 microns in thickness. Then we get down to some thin film deposition, where something I love doing. So here we chose to use atomic layer deposition. In the system you can see here, it's from the Finnish company Picosun, and the samples are loaded in through this glove box. We don't need the glove box in our application because our samples are air stable, but some of the other materials being handled here are not. So for those of you unfamiliar, atomic layer deposition is a layer by layer coating method based on a simple hydrolysis reaction. And we chose to use atomic layer deposition because you get very precise thickness control down to the angstrom level. And it is possible to achieve conformal coatings. So this means following the contours of your substrate. And thus for us, meaning the challenge, maybe we can even get the thin film deposition happening inside the membrane pores. So the first step now, preparing our membrane. So the membranes are commercial, off the shelf. We're just making them photocatalytically active. But first step was to deposit a thin, that means less than 1 nanometer thick, aluminum oxide layer. This is just a recipe that was taken from the literature because it is known to reduce the amount of surface defects that are present in these membranes after the manufacture process. It was just a bit like a barrier layer, I would say. For this, we use trimethyl aluminium as one precursor. That's our aluminium-containing precursor. And of course, for a hydrolysis reaction, the other reactant that we need is water. These are transported through using a nitrogen carrier gas at 250 degrees C, pressure is 3 millibar. And then what you're doing with ALD is this typical cycle that I've shown in the bottom right-hand corner. So you have a very short pulse of your precursor. Here it's only 0.1 second long. Then you have a purge time, which then allows the purging of the gases from the system. And then you introduce your other precursor, in this case, water. And then on the substrate, you have the water molecule going in, finding the trimethyl aluminium molecules that are on the surface, and then a reaction taking place. And then byproducts, which are in this case mostly methane, shown by the equation at the bottom, being given off. And you're repeating this endless, or not endless number of cycles, but up to hundreds of times to get appreciably thick films. So that's the principle of ALD. The key material for our work was titanium dioxide as the photocatalyst, and for that we used a titanium tetrachloride precursor. So here again, it's just the simple reaction with water forming our titanium dioxide. The deposition conditions were the same as I described to you before, so 250 degrees C is the substrate temperature, and we're doing somewhere between 50 and 500 cycles of this material. Now, because the temperature is relatively low, this gives us an amorphous titanium dioxide, which we don't want. We would prefer the more photocatalytically active phase of anatase, and that we achieve by annealing for 400 degrees C in situ. So after the deposition condition is done, we raise the chamber temperature up to 400 degrees C and giving us a conversion to the anatase phase. And as I've shown on the right, there are some small peaks in the top black XRD diffractogram which line up with the presence of anatase shown in red from the reference database. Not strong because these films are very thin. And then we have look at what is the goal of this. So we're trying to understand the conditions that maximize the efficiency of our photocatalytic destruction of our organic pollutant in aqueous solutions. So for us, this is our methylene blue in water, using our titanium dioxide coated membranes in the single pass flow through mode. So we're varying 3 material parameters, as we call them. 2 of them we don't have a great degree of control of. So there's 2 suppliers of the membrane. There's 2 different pore sizes of the membranes available each. And then what we do have quite good control over is the titanium dioxide coating thickness. And then on the right, we're going to look at varying 3 different experimental conditions. The flow rate, passing to the feed flowing through the membrane, the concentration of methylene blue, and the intensity of the ultraviolet light. And then just bringing all that together in one graphic down the bottom, you can see you have your light coming in on the stainless steel cell, which you wouldn't normally see. This is the bottom half of it. It would normally be sealed. In there is your membrane with the cylindrical pores. It's now, hopefully, as shown on the right-hand side, being coated with red, which in this case would be the titanium dioxide, and this enabling a photochemical destruction of a methylene blue molecule. So starting with some materials characterization of the thin films. So we were commonly using X-ray reflectance as a measure of the thin film thickness. But I should emphasize here the thickness we're measuring, shown on the top right, is the titanium dioxide film as deposited onto a polished silicon wafer. So it's not on the membrane, it's on a flat surface, the polished. And there the graph shows that you have a very linear relationship between the amount of cycles and the film thickness. So we can get anywhere with our process between somewhere like 2 nanometers thick as being the thinnest, up to about 14 nanometers as being the thickest films. The absorbance, the optical absorbance of these materials were measured by placing the membrane inside a water-filled cuvette, and then that being placed inside an integrating sphere in a spectrophotometer. And there we were measuring the effective absorbance at 365 nanometers. And what you see on the bottom right-hand graph is the 2 different membranes and the 2 different pore sizes. But you see that there's actually not a strong difference. All of them basically follow a trend that we deposit thicker films, and apparently the thicker films also correspond to a larger amount of light being absorbed. But this we found interesting because if you have to remember that we're only depositing typically 5 or 10 nanometers of titanium dioxide. So we didn't expect the absorption to be so strong. And that's why we did this method of putting the samples inside the integrating sphere. And we were able to determine that actually because of the structure of our membrane, we're getting typically the amount of light absorbed that you would expect from a 3.5 micron thick planar film. Now that's 300 times thicker than actually what we have. So this was the first evidence to us that, okay, the titanium dioxide is probably inside the membrane, light is being scattered around and therefore much more effectively absorbed than you might think. And that's what we then started investigating next. So the hypothesis on the right with the question mark is shown here. So do we get this yellow region, which would be titanium dioxide, on the green, which is our membrane? Is it all coated nice and uniformly like that? Well, not quite. So we used energy dispersive X-ray spectroscopy, EDX, to do some cross-sectional analysis. And shown in the bottom right-hand corner, you can see the images for titanium. So where you see bright green present, this is where there's a large amount of titanium present in the cross-section of the membrane. And for example, if we take the top left, the Wattman 200 nanometer system, you can see there's a large amount, maybe going through to about halfway of titanium present, and then nothing near the rear. And if we go to the bottom right-hand corner on the smart membrane, you can see actually there's titanium on the front and the rear, but not in the center of the membrane. This probably occurred because of the membrane lifting up at the edges during the deposition. The membranes are relatively brittle and are not so mechanically stable. So in the bottom left-hand corner is actually a rough schematic of what the membranes more look like with their titanium dioxide coating. There is a large amount on the top surface, and then reducing throughout the thickness of the membrane structure, with possibly some titanium dioxide being deposited onto the rear. So we were looking at degrading methylene blue, the chemical structure which is shown here. And a lot of the times from now on in the proposal, in the presentation, I'll talk about removal. And this is the concentration of the methylene blue measured as it's going through the spectrophotometer compared to its initial concentration, so CMB 0. And you can see here, shown in the graph, we have a dark phase initially. This is just to allow the system to equilibrate, and any methylene blue that might be want to absorb in the system can. Then at time 100 minutes, which corresponds to a volume of 50 milliliters being passed through the system, we turn on our UV LED, and then you can see two curves. So the solid curve is dropping quite steeply. That's for our titanium dioxide coated photocatalytic membrane. So this is achieving about a 60% removal in this example. But what I'd also like to highlight here is the dotted top curve. So the dotted top curve is the pristine membrane only with no titanium dioxide present. And the fact that there's no removal here indicates strongly to us that there is no photolysis reaction of the methylene blue. Thus, the methylene blue here is only being destroyed in the presence of the titanium dioxide. Then we start to look at some other parameters. So the first one we looked at was the function of thickness for the different membranes. So Wattman 200 nanometers, Wattman 20 nanometers, smart membrane 200 nanometers, smart membrane 20 nanometers. And on all graphs, the y-axis is the methylene blue removal. So although there are two distinct membranes with two different pore sizes, we didn't see a strong trend in the amount of removal varying. Some performed slightly better than others, but in the end, we chose the smart membrane 200, which is the graph in C, the bottom left-hand graph, as the one to proceed with all future experiments. So here, we also, you can see that there was a peak performance at about 12 nanometers. Excuse me. I wouldn't trust the values going higher than this, as 15 nanometers therefore being worse. What did happen after 12 nanometers though was that the membranes did become very brittle and they cracked a lot. So the mechanical handling of these membranes for thicker titanium dioxide coatings was terrible. This was another reason to stop at about 12 nanometers. Then we look at just taking that one membrane. We look at increasing the membrane flux. So this is the flow rate through our system. And you can see by doing this, increasing the flux up to 600 liters per meter squared per hour, you can achieve residence times shown on the top x-axis of somewhere in the range of 0.1 to a handful of seconds. And these are relatively fast residence times for photochemical reactions. So here what we're showing is that you can get up to about 80% removal at the lowest flow rates, dropping down to about 30% at higher flow rates. If we look at the photocatalytic removal of methylene blue as a function of light intensity, we see quite an interesting trend. So there we see a very steep rise in the performance, go up to about 2 milliwatts per centimeter squared. And then after that, it's relatively flat out to 25 milliwatts per centimeter squared. So obviously the availability of light is not our main problem here. It's not limiting our performance. Now I'd like to highlight that this amount of light, 2 milliwatts per centimeter squared, is roughly half what is available in terrestrial sunlight. The terrestrial sunlight, if we look at the AM global spectrum, has about 3.65 milliwatts per centimeter squared, as shown in the bottom left-hand graph. So with roughly half a sun, we're able to achieve good degradation. Some conclusions drawing near the end here. So atomic layer deposition was able to coat, let's say, roughly the top half of our 60 micron thick ceramic membranes with titanium dioxide. Only 12 nanometers of titanium dioxide was required to achieve 90% light absorption. And with this membrane's single pass degradation of methylene blue was achieved with typically something like a greater than 60% removal. We demonstrated that the membrane, the methylene blue removal decreased with the increasing flow rate and the methylene blue concentration, but the reaction rate, which actually I didn't discuss, probably due to a slight time constraints here, does increase. Finally, a significant photodegradation, greater than 50% removal, occurs with just over 1 sun's worth of UV light intensity. I have a handful of more slides just as highlights at the end. So this is parallel work ongoing for us, is the work at visibly active organic photosensitizers. This is driven by a chemist in my group who is an expert on porphyrins. So these we are also coating onto polymeric membranes with the advantage that they exhibit strong visible light absorption. And future work where we would like to head with all of this, because we realize this is very much early days for us. Atomic layer deposition is something I'm very passionate about, and it looks to be working very well. We would like to optimize the process such that we can coat the entire membrane thickness, starting with titanium dioxide. Then we would like to look at modifying the titanium dioxide to achieve visible light absorption. So strategies here include doping the titanium dioxide, deposition of other photocatalytic oxides. Lars was talking about copper oxide, zinc oxide, etc. These would all be possible via atomic layer deposition as well. Also as multi-layer stacks could be interesting. We're moving away from using these dyes to using real environmental hazards in water, such as micropollutants. So examples here are pesticides or hormones that may appear in wastewater streams and are often poorly removed. And then a large problem about photocatalysis is also the scale up. So enhancing the light absorption to be able to enhance the flow rate is a goal. We would like to move up to a 5 by 5 centimeter system. That's away from the current 25 millimeter diameter system. And with that, you can see in the bottom right-hand corner, there's an orange and white box. This is our nice solar simulator based on 22 LEDs that can simulate sunlight over that area, which would be sufficient for us. Long-term stability measurements will still need to be done. At the moment, we have tested for 30 hours and have seen no changes there. And ultimately, switching to polymeric membranes would be of interest to the water treatment community because they are not commonly using ceramic membranes. Finally, a little bit of, let's say, bridge building. Yeah, but I have a strong passion for Africa, and I'm always looking to build partnerships with Africa. Since joining KIT, I now have got KIT signed up as a corporate member for the African Network of Solar Energy. There are a lot of German initiatives coming through for funding joint projects. So this is with our Federal Ministry of Education and Research, particularly in West Africa for that government department, and also the German Research Foundation, where currently Margaret Samiji and Msseesa Diale from University of Pretoria and myself are pushing proposal. PhD scholarship opportunities exist. The German Academic Exchange Service, the DAD, is quite generous in providing 4-year scholarships to study PhDs in Germany. And also KIT is also a member of the PASET Regional Scholarship and Innovation Fund. This may be known to our Kenyan friends. It comes from ICHIPE, which is one of the insect and malaria research organizations based in Nairobi. And KIT is a partner here as well in the Sandwich program, where you can spend 2 years in Africa and 2 years at KIT. And with that, I would like to briefly acknowledge funding from the Helmholtz Association for this work, and to say a very big asante sana to the organizers for the opportunity to present. Thank you all for your attention, and if you have any questions, I'll be happy to take them. Thank you. Your microphone, Julius.
Thank you very much for that presentation, Professor Richards. Now the floor is open for questions and comments. Please introduce yourself and say where you're from. Yes, any questions or comments?
Lars Östlund, Uppsala University here.
Hi, Lars.
Yes.
Hi. Thank you for your nice presentation here. I love to test our materials in your reactors. And this is my first.
Me too.
That's my first comment, actually. But I have a question. In your membranes, I like this concept. Have you tried to use the wet chemical deposition methods just to impregnate your membranes as a reference?
No, but you could. I mean, you could easily. You could try and take a sol gel approach as well,
yeah.
if you wanted to. Yeah, it's something we've thought of, but simply not enough students and to match the ideas. It would possible. Okay. Yeah, for sure.
Yeah, thank you.
Any other comment? We still have 15 minutes for questions and answers.
Hello, I'm Jakob Tyr from Uppsala University.
Yes.
I had a question about the atomic layer deposition. When you flow the precursor gases to the membrane, it flows above the membrane and diffuses in, or does it actually flow through the membrane?
Good question, Jakob. Thank you. So at the moment, the gases flow into a manifold inside the chamber, and then are simply dispersed due to the low vacuum. So at the moment, we are somewhat constrained by the diffusion process into the thick porous structure of the membrane. If you could modify the ALD deposition system, it would be much better or more effective to have it flow through the membrane, which would be let's say the physics approach to doing what Lars just asked a question about, of doing it via the wet chemical approach. So, brief answer to your question, at the moment, the diffusion of the precursors is very much likely limiting the formation of titanium dioxide in the center of the membrane.
Yes, thank you.
Thank you.
Julius here from University of Nairobi. Richard, can you please explain a little bit on measurements of thickness measurements using X-ray reflector in terms of equipment and principle?
Yeah, so here, if I go back to slide, what is it, 18? So I mean, here we have a so we have different opportunities to measure the thickness of the material. X-ray reflectance mightn't appear to be an obvious choice for doing this. However, it happens to be in the same lab as the atomic layer deposition system. Myself, with my background in optics, I would also actually quite happily measure ellipsometry for such thin films. But the problem is here that the films, we're not always sure of their exact chemical nature. So whether they are fully anatase or whether they're partially amorphous still, or perhaps if you go to higher temperature, you will get rutile present. So there you might get a mixture which would cause problems with your refractive indices. So by using X-ray reflectance, which is like X-ray diffraction, just in a modified geometry, we're just looking at the elements as they're stacked up in the planes, and then getting information about that. And then, like I said before, this was all measured on a polished silicon wafer, and from then on, when I'm talking about thickness, for example, in the bottom half of this graph, the thickness here on the x-axis is the planar thickness, but of course the measured absorption here is effectively much greater because that is deposited inside this porous substrate. Yeah, so it's I should probably be a little bit clearer and call this, let's say, a nominal thickness, because it's not the thickness as measured inside the membrane pores, it's the thickness on a polished silicon wafer. Apologies if that was, yeah, it's a little bit misleading how I've presented it.
Thank you.
Okay, thanks, Julius.
Yeah. Any other questions, comments?
Yes. My name is Roshana. I have a question. Why did you deposit CO2 on polysilicon wafer compared to other substrates? And did you consider about the reaction with the silicon?
I'm not sure if can you rephrase your question, Eva? I mean, I understood it's about titanium dioxide and the silicon wafer, but what is the question exactly?
The question is, why did you choose that as your substrate compared to others? And did you consider about the reaction with the silicon?
Okay, so the silicon wafer was only used for these thickness measurements. So it was placed, pieces of polished silicon wafer were placed next to the membranes inside the ALD deposition chamber. So that's just for convenience, because the silicon is atomically flat and polished wafers are very easy to measure. The answer to your second part of your question, from my PhD, I know that you will get some interactions between titanium dioxide and silicon, especially interface. You can get typically a mixed kind of silicon titanium oxide forming. If that is of interest, I can answer maybe more questions about that offline. But in our case here, this wasn't really of interest, since the host membrane is made of aluminium oxide. Yeah, so but if you're interested in silicon and titanium dioxide interfaces, this is actually what I did my PhD in Australia, with the application of solar cells. And there I can tell you, yes, you get some, I've observed some intermixing at the interface, especially when you go to higher temperatures. By higher, I'm meaning 1,000 degrees. Yeah? Here we only went to 400 degrees C. Okay. Thank you.
Yes. Any more questions or discussion?
I have one.
Yes, kindly introduce yourself, please.
Yeah, my name is Robinson Msembi from the University of Nairobi. I just wanted to know whether titanium tetrachloride is the same like titanium isopropoxide?
It is a different chemical precursor, but I have used titanium isopropoxide in my PhD as well for formation of titanium dioxide, and I would say they both work equally well. I used titanium tetrachloride because it was available on our atomic layer deposition system. I believe probably the main differences are going to be, some of them are going to be in terms of the byproducts formed. So I think here you have actually a hydrochloric acid as a byproduct of the reaction. But from the dioxide point of view, I haven't observed great differences between starting with one precursor or the other. So you could use either.
Okay, thank you.
Yeah, thank you, Robinson.
Okay. I think we can also use the time, because we had two keynote speakers. We can use the time to ask questions to either both Lash or Bryce.
Maybe I will actually go back a slide and ask a question to some of our East African attendees. So in the middle here, I've mentioned this German Federal Ministry of Education and Research. They have very strong links into West Africa that was started by the formation of WASCAL. This is this climate change initiative. And I was wanting to ask you, is there a similar equivalent body in East Africa that we could somehow utilize to build these bridges? Because they seem very keen on these bridges via the climate change initiatives. Can any of you make a comment?
Professor Duda, maybe Professor Duda can comment.
Perhaps there's an addition. I mean, I think I saw that they must exist in Southern Africa. I think there is a SASCAL, but I didn't find an ESCAL for the East Africa option.
I don't know if anybody is ready to answer that question.
That's okay. I will just leave the question in the room and we can think about it.
Maybe put it on the chat. Maybe put it on the chat, and then somebody may.
Yes. Good idea.
Yeah. Now, there's a question I'm seeing here on the chat from Eva Tito Shana, and she says, I think you answered that question. How does silicon and TiO2 interface affect the film at room? I think she meant room temperature and higher temperatures. I think you answered that question.
Okay, yes.
On the chat, yeah.
Mm-hmm.
Yeah, then I think if we don't have any other question, I want to thank both Professor Bryce and Professor Lash Osterlund for the very nice presentation. And kindly feel free to continue with the attendance for the conference. We will go on until Friday.
Mm-hmm.
And yeah, and it would also be good for the students to switch on their cameras so that we can see them. Some, I'm sure I know some are having issues with the network, but I think if the network is okay, you can switch on your camera so that we can see you. Yeah, so that we can take a picture of all of us when we are online. Otherwise, I think I would want to go to the next topic. I think we have saved like 10 minutes. We want to go to the next presentation. And the next presentation is going to be by Miss Mary Tabu, Are you around? Miss Mary Tabu?
Yes, I'm around, Prof.
You're around? Yes, okay. And she's going to talk to us about an assessment of the use of static magnetic field for sodium fluoride defluoridation and removal of Escherichia coli and rotavirus pathogens from water. You have 15 minutes. Kindly continue, yeah. Yes, Mary, please welcome.
Yes, I'm
Okay.
I'm sharing the screen.
Okay.
I hope you are seeing the screen.
Yes, we can see the screen. Maybe put it on presentation mode. Yes.
Hello, I'm Mary Tabu from the University of Nairobi, the Department of Physics. I'm a PhD student working on water purification. Today I'm going to present one of our papers that we are preparing, titled An Assessment of the Use of Static Magnetic Field for Sodium Fluoride Defluoridation and Removal of Escherichia coli and rotavirus pathogens from water. The sponsors for my PhD have been GATS Magnet Fund, International Science Program, and Kenyan National Research Fund. My supervisors are shown below. The World Health Organization predicts that at least one person dies every 26 seconds due to waterborne diseases. 90% of these deaths come from the developing world, especially Africa. 80% of the deaths are innocent infants. Because of these challenges, a lot of research has been focusing on water purification. And this has focused mainly on the following contaminants: bacteria, viruses, protozoa, and also in East Africa, we suffer from the challenge of sodium fluoride due to the high levels from the deposit of the Great Rift. So these have made many research to come up, and we have come up with many purification systems, such as use of chemicals, filters, and ultraviolet light. Use of chemicals, as especially such as chlorine, which is used in most of our municipals, leave byproducts which are also harmful to our bodies. Filters such as reverse osmosis and ultrafiltration are quite efficient. However, they are too costly for the developing world, and also sometimes they overfilter the water and remove the important ions such as sodium, which are useful to the body. Clay ceramics, which is part of my work as a PhD student, we have seen that they are brittle, and in my work I've been trying to improve their mechanical property. Sorry. Because of this, there are so many research and entrepreneurs who have invested in use of magnetic field for water purification, and these have been applied in the pipes, in industries, and even in water pools. However, there is we have not found somebody who have really worked on this water purification of the pathogens we just mentioned in the earlier slide in water. They have, like Tobas has worked on them outside the water environment, has worked on E. coli, and found out that indeed magnetic field reduces the the growth of rather the multiplication of E. coli outside water, but none of them have tried in water. So that's the very reason why we took these contaminants and put them in water, and to see if the same effect they have observed outside the water will be felt inside water. So in our work, we used E. coli. We inoculated E. coli on a plate using cysteine lactoso electrolyte agar at 37 degrees for 24 hours. And we were able to take the inoculated E. coli and put it in water, contaminate it, the water with it, and the concentration of it varied from 10 power 1 colony forming units to 10 power 8 colony forming units. We then passed this contaminated water in through magnetic field, and we used a cylindrical magnetic field of 1 Tesla. We tied them around the pipe of 1 meter at an interval of 10 centimeters apart, and then circulated the water through the filter at different velocities. We also varied the concentration of E. coli and sodium fluoride. We also tried the same procedure with the rotavirus, and we were able to find out that the pH of the ionized water decreased with an increase in the circulation time, as shown in the figure, because the static magnetic field made the water acidic by enhancing its OH bond. The pH was found to reduce most in fluoridated water because sodium fluoride forms its constituent ions in water, which align themselves in the presence of external magnetic field, causing the decrease of pH. Escherichia coli, on the other hand, produced acidic waste, Schenker toxin, that reduces its pH, and it reduces the pH of the water. However, the same bacteria uses in the proton form the toxin that it has produced for transportation of minerals. That is why the observed slope of pH is lower than the one observed by sodium fluoride. The pH of rotavirus coincided with the one of ionized water, as shown also, because the multiplication of rotavirus particles involves the mechanism of transportation of proteins, which leads to the buildup of viral protein in viroplasms and does not affect the pH of its surrounding. We also found out that the replication of Escherichia coli decreased with increase in circulation. Increase with increase in circulation as time has shown, because the cells of the bacteria subdivide continuously, forming new cells, and the presence of static magnetic field slowed down the replication of the bacteria, because the production of the oxygen-free radicals in water by magnetic field made the water slightly acidic by enhancing the hydrogen bond and kill the pathogens. In the process of magnetic field, the molecules aligned themselves to the applied magnetic field, which in turn affected the embedded ion channels, altering the activation kinetics. Furthermore, the magnetic field affected the behavior of the long-lived ion quantum states, causing an imbalance in ion protein stability, which resulted in the death of the pathogens. The replication of rotavirus also increased with time due to similar reasons, and the presence of the static magnetic field also slowed down the multiplication. And on the effect of temperature, we saw that an increase in temperature increased the enzyme activities, which in turn increased the protein activities essential for Escherichia coli growth. That is why the replication of the bacteria increased continuously from 16 to 37 degrees Celsius. However, from 37 to 40 degrees Celsius, the protein phases became saturated, and there was no increase in the number of bacteria when the temperature of the water increases, because the activities of the bacteria are enzyme sensitive. The growth of rotavirus was found to decrease with an increase in temperature, just as it was reported in literature. An increase in the ambient temperature caused the outer envelope of the virus to melt to a liquid phase, thereby slowing down the multiplication of the virus. This liquid form phase allowed other elements of water to mix with it, causing the death of the virus. On the other hand, sodium fluoride increase in temperature increased its pH, because the more the temperature increased, the more the sodium fluoride dissolved in water and therefore increased its pH. We also found out that in the first around 3 or 4 hours, Escherichia coli and rotavirus increased, its efficiency increased rapidly, because the organisms had not adjusted to living in the effects of magnetic field. These effects, as we have mentioned earlier, include pH, change in pH, instability in the ion-protein ratio in the embedded ion of the organism, and the change in kinetics of the organism stability. Further exposure to the magnetic field allowed the pathogens to adjust to these changes, resulting in the reduced purification rate. Similarly, the defluoridation curve was steep around the same time, because most of the sodium fluoride molecules were not aligned to the applied static field. But as the fluoridated water continued circulating, the molecules got fully aligned to the applied field, causing increase in acidity. Using the optimal temperatures, that is 37 degrees Celsius for E. coli, 16 degrees Celsius for rotavirus, and 40 degrees Celsius for sodium fluoride. At a time of 9 hours, the magnetic field was able to reduce by 14% in sodium fluoride, 9.8% in E. coli, and 7.1% in rotavirus. The concentrations of the contaminants after 9 hours were 8.6 milligrams per liter, 4.1 times 10 power 5 colony forming units per milliliter, and 4 times 10 power 3 viral particle per liter for sodium fluoride, Escherichia coli, and rotavirus, respectively. So the above concentrations are way above the recommended levels. As we know, the recommended levels for sodium fluoride are 1.5 milligrams per liter, and then the one for E. coli we actually need more than 99.9% efficiency in purification, and the same thing for rotavirus. So we can therefore conclude that this work has shown that the use of stationary magnetic field in water purification, defluoridation of water by 14.1%, and slows the growth of pathogens by 9.8% and 7.1% in Escherichia coli and rotavirus, respectively. However, this technique does not defluoridate and purify water of Escherichia coli and rotavirus to recommendable levels. We therefore recommend that this technology be used along other techniques to purify water up to the World Health Organization standards. Thank you. Hello.
Yeah, thank you for that presentation, Mary. We are going to go to the next presentation. And after these two presentations, then we will have a question and discussion time for both the presentation. So now we will take the presentation by the next presenter, that is Ngei Katumo. And I'm informed Ngei Katumo is not there.
No,
So,
hi, it's Bryce here. No, sorry. So Ngei is my student.
Yes.
But he is not able to present. I think he let you know this via email.
Yes, I've just been informed that by Victor that he's not able to present. So then I will then ask Professor Mobora to maybe allow questions now for Mary as we look for an alternative presenter for this time period. So we can have questions and discussion meanwhile.
Mary, I have a question for you.
Yes, Prof.
So what do you think is the potential for the scaling up of your technology if you're with the reliance on magnetic fields? What can you say about that?
I think if we increase the if we increase the magnet strength and also use like alternating current, alternating magnetic field, and also increase the time, I think we'll get better results.
Okay, cool. Thank you.
Yeah.
Chair, I have a question.
Kindly introduce yourself.
Yeah, my name is Professor Musembi from Department of Physics, University of Nairobi.
Yes.
Yes, I have two questions for presenter. One of them, the last while she is she was answering the question from the first person who has asked the question. I don't know why she would say she wants to increase the magnetic field, because she has already said she was using a magnet of 1 Tesla. You know, that is a very huge magnet. That is 10,000 Gauss. And when you look at magnetic resonance imaging, they normally use around 0.5 Tesla to around maybe 3. And you know, those are very big equipment. So 1 Tesla, I don't think whether it needs to be even increased further. That is a very big magnet. The other question is on when she puts the title as static use of static magnetic field for sodium fluoride defluoridation. Us as the audience, we were expecting to see, because this is not, this is the physics, it's not mainly engineering, because she has talked about mainly about how the work was done and what. But also, as a physicist, we should have also seen how she has applied these things like the Maxwell's equation, the Gauss law in magnetism, the Maxwell-Ampere law, the Faraday law, the boundary conditions, because this magnet is interacting from one surface to another surface. How is that surface affecting the magnetic field, applying the boundary problems, the conditions, those kind of things? We would like to see them as a physicist. I don't know, what is the answer from the presenter?
Okay, thank you so much, Prof, for your question.
Mary, there's also a question on the chat. So maybe...
Can I answer this too first, then we go to the chat?
Yes.
Okay, why I suggested increase of of the strength is because some of my counterparts have used more than that strength, and they have maybe they have found better result, and but as I said, most of them have not worked with the pathogens inside water. They have used pathogens, worked with pathogens outside water. But me, I was using inside water, and I was not able maybe to access such high magnetic field, and it's also not very good for our body, that high strength. But other researchers have used stronger magnets. Now, because of the presentation, maybe I was not able to go into much details of the theory because of the time given, but we know water is a diamagnet, so we are going to apply all those theories you are bringing across, and they are the ones bringing about all those effects. So maybe in my next presentation, I will make sure that I touch on the theory. So thank you so much.
Just before you go to the other question from the other in the chat, you have suggested that maybe in the future you are going to use you are going to introduce alternating current. Also, when we are writing the Maxwell's equation, we write them in different ways. There are those Maxwell's equations, we write them in the applicable in the vacuum for conducting media, for non-conducting media. And then when you start introducing the alternating current, now we introduce the space and the time. Now they become a bit different because we can write Maxwell's equation in 4 different ways. So the time when it reaches for you to introduce the alternating current, also you're allowed to rewrite the whole thing because the interaction will also be different. It will not be the same like the static one. The static one is like at 0 Hz. But now when you introduce the alternating current, now there will be frequency because now there will be R and a T. Okay, thank you.
Thank you, Prof.
Yes, Mary, there's a question on the chat. I don't know if you can see that question.
I'm on the slides. If you can read for me, please.
Yeah, from Saingasa. And she's asking, or he's asking, what could be the possible mechanism for slowing down E. coli and rotavirus? And that is Saingasa from University of Dar es Salaam.
Okay, I think I answered that question when I was mentioning on the its growth. That was around when we were handling the time, and let me go to that slide. Sorry, I had gone somewhere else. So there are so many things that can cause that. Am I at the right place? That was, I think, this slide. So the presence of static magnetic slows down the replication of the bacteria because of the production of oxygen-free radicals in water by magnetic field, which made the water slightly acidic by enhancing the hydrogen bond and kill the pathogens. And in the presence of magnetic field, the molecules get aligned and get aligned themselves to the applied magnetic field, which in turn affects the embedded ion channels, altering the activation kinetics. We also know that the field affects the behavior of the long-lived ionic quantum states, causing an imbalance in ion protein stability, which resulted in the death or slow down the growth. I don't know if I've answered the question.
I don't know if Sai is present, if he's happy with your answer. But if he's not, I think he'll put in another comment. We still have 20 minutes, but if there is no question, we will move to the next session 2, that is going to be chaired by Dr. Dennis Okello, and rapporteur will be Dr. Alex Ogacho. If they're ready, they can take over.
Yes, Chair, before you hand over.
Yes.
The last answer from Sister Mary, when she spoke of the quantum state, I would advise her not to go to that one, because she can continue treating a system in the macroscopic media. Because if she goes to microscopic and go to the quantum mechanics, she will have to start solving things like electron spins, and that one will be very difficult. But if she continues to solve the problem in the continuous media, it will be far much better and easier without complicating the problem. So the last answer, she should desist from moving in that direction. Thank you.
Okay. Okay, I think Mary, you've had the comment. Now, presentations, specifically Professor Lars Osterlund and Professor Bryce Richards and Sister Mary. And now we would like to move to the next session, and this next session is going to be chaired by Dr. Dennis Okello from the University of Makerere. Dennis, please welcome.